Hi there and welcome to this IB Maths Intense session on exponentials and logarithms. Having just been introduced to the laws of logs and what logs are, we're now going to be looking at how we work with the laws of logarithms to simplify expressions or to express things in a slightly different form. Just gentle reminder, you've got some of the laws of logarithms expressed there on the formula sheet, so you don't have to learn them all, but it always helps if you do. But we're going to be using these and derivations of them in the following examples. So what might we be asked to do? Well, we might just be asked to simplify expressions that using the laws of logs we can simplify. In these first four questions, hopefully if you understand what a logarithm is from our first session on logs, you can see these purely by looking at them or by inspection. Because when we look at an expression that says log to base a of b, we're asking, what do you raise a to the power of? A to the power of something equals b. So in this first question, what do we raise a to the power of to get a to the power of 5? Well, we raise it to 5, to the power of 5. In other words, a to the n has to equal a to the power of 5. So in this case, a to the n must be equal to 5. So we've answered the question there in terms of what do we raise a to the power of to get a to the power of 5. The second question, we're saying a to the power of something, I'll write it down over here, a to the power of n has to equal square root of a. Well, the square root of a written in power form, of course, it's a to the power of a half. So the answer here is just simply a half. A to the power of a half equals a to the power of a half. In the third one, my base this time is root a. So in other words, my base is a to the power of half, and I'm raising that to the power of something to get an answer of a to the power of 6. A little bit more complicated. So it's saying, what do I raise root a to the power of to get a to the power of 6? So in this example over here on the right, basically a half n would have to equal 6. That means n would have to equal 12, because a half times 12 would then give me 6. So my solution here is 12. And this final example, I'm going to have to deal with both of these separately. The first part, log to base a of a cubed, exactly like example A, well, that's just going to be equal to 3 because I raise a to the power of 3 to get a cubed. The second part, a little bit more difficult. Let's just write that down. A squared, what do I raise that to the power of? Oh, so a squared to the power of n to equal a. Well, a is a to the power of 1. So 2n has to equal 1, so n must be a half here. So the solution to the second part of that is a half. 3 minus a half equals 2.5. So log to base a of a cubed minus log to base a squared of a is 2.5. This will come just with practice and understanding what we're being asked when we're asked for a logarithm. And these you can see probably just by inspection. We'll often be asked to bring together a number of different logs and express them as a single logarithm. And the key here is to use the laws of logs and to just start gluing bits together. So in this first example, log 32 minus 4 log 2 plus log 20. Let's just start gluing bits together. Log 32 and then 4 log to base 2 is the same as log to base 4 log 2 is the same as log 2 to the power of 4, which is log 16. And then we've got log 20 to add on there at the end. Well, our laws of logs from below here, the subtraction one here, log 32 minus log 16 is log 32 over 16, which is log 2. So we've already merged together two parts of that expression. And then log 2 plus log 20 is the first one of these laws here. We can bring those together to create log 40. Now, of course, if you wanted to be really smart there, log 40, we're in base 10 now, is log of 4 times 10. And log to base 10 of 10 is 1. So that equals 1 plus log 4. But I don't think it matters if the question says express as a single logarithm. That's exactly what we've done there, log 40. The second example is a good one to show you because sometimes we'll end up with an expression which has got a log in it and a number, but if we want to express them together as a single logarithm, we have to put the number back into log form. So this one, log to base 3 of 36. Now, remembering what we said on the previous slide, what we're asking here, to get an answer of 2, I'd have said, when I raise 3 to the power of 2, what do I get? I get 9. So 2 is equivalent to log to base 3 of 9. Hopefully you can see that, because when I raise 3 to the power of that 2, I get 9. That's the link between the numbers. And then I can just use the second underlined law there to bring these two together. This is log to base 3 of 36 over 9, which is log to base 3 of 4, 36 over 9. Nice and straightforward. The final one, I've got an expression, a quarter log a to the m, which is fairly straightforward. But the second part, I really want to split this out so that I can then bring bits back together again. At the moment, there's no real opportunity to do that because I've got a quarter log m and then I've got 3/4. So I'm going to split out the second bit. So I'll end up with a quarter log a to base m. And you'll see here I get 3/4 log a to the m. That's nice because I can then join those two up. And then I must have also 3/4 of log a to the n to the power of 4. And so I can join the first two bits and I just get log a to the base m. Remember, my end game here is to have a single log. And the second bit, I've got 3/4 log a to the n of n to the power of 4. What I can do is I can bring that power up and I get log a of n to the power of 4 to the power of 3/4. Well, 4 times 3/4 is 3, so I end up with log a to base m plus log to base a of n cubed. And then I can bring those together because that additive rule down here. So I end up with log to base a of m n cubed. And I'm going to put that in brackets there just to show that that's all together. So I've done what I've been asked. We've got a single logarithm there. This is a popular question. I've seen there's a lot in different textbooks where we're given an expression x equals log to base 10 of a and y is log to base 10 of b. And we're given an expression that we need to rewrite in terms of x and y and any integers that happen to be left over too. So our tactic here is to split this out as best we can so that we end up with log to base 10a and log to base 10 of b on its own, so we can replace it with x and y. So let's have a go at doing that. Log to base 10 of 1000 a cubed. And the first thing I'm going to do is I'm going to do a subtract here and subtract log to base 10 of b squared. That's just using the rule down here about division, and that immediately gets log b squared on its own. The first expression, I've got log to base 10 of 1000 a cubed, so I'm going to split that out too. So I get log to base 10 of 1000 plus log to base 10 of a cubed. And I've still got subtract here, my b squared. Now, I can do three things here. Next move, log to base 10 of 1000. Hopefully you can see that, what do I raise 10 to the power of to get 1000? Well, it's 3. 10 to the power of 3 is 1000, so I can replace this first bit with 3. The second part, log to base 10 of a cubed, I want to get log to base 10 of a on its own, so I'm going to bring the 3 to the front. Using this rule here on the formula sheet, I can bring the 3 to the front. 3 log to base 10 of a, and similarly here, I can bring the 2 to the front, 2 to log base 10 of b. And then I've answered the question because that gives me a mixture of integers and x and y. 3 plus, well, log to base 10 of a is x, so I've got 3x and log to base 10 of b is y, so I've got 2y here. 3 plus 3x minus 2y. Nice and straightforward. Just go step by step and split out the expression so you end up with log to base 10 of a and log to base 10 of b. In a similar manner, but this time with numerical values rather than algebraic, we're often asked to split things out and find an expression in terms of, in this case, log to base 10 of 2 and log to base 10 of 5. And this is just about finding a way of expressing the number you're given in terms of the numbers you want to get to. So log to base, this is all in base 10. Log of 10 is simply log of 2 times 5. And we know that we can split that out to make it log of 2 plus log of 5, just using the first of the rules there on the formula sheet. And I've got my a and b there. That's just a plus b. Nice and straightforward. 250 a little bit more difficult, but I know that 250, certainly I can get 2 out of there. It's 2 times 125. So to start with, that's log 2 plus log 125. But hopefully we also know that 125 is 5 cubed. So I've got log of 2 plus log of 5 cubed. And I can bring the 3 to the front. Log of 2 plus 3 log of 5. I've now got that in terms of a and b. That's a plus 3b. This bringing down of the power to the front is extremely useful, and you'll do that a lot in order to simplify expressions. Log of 0.4, don't be scared by the fact that it's a decimal. My knee-jerk reaction whenever I see it as a decimal is to put it into fractional form, because then it's easier to see a pattern in numbers. So this is log of 4/10. Doesn't really help me in terms of 2 and 5, but I do know that if I simplify the fraction, I would get log of 2 over 5. And then this has opened up the question. Log of 2 over 5, using the second of the rules on the formula sheet, is log of 2 minus log of 5. And sure enough, that's in terms of a and b now. A minus b. And we'll do something similar with the final example here. Let's make that into a fraction. Log of 8 over 100. Well, can't see 2 and 5 immediately, but if I simplify that fraction, I'll get log of 2 over 25. So I've nearly got it. Log to base 2 minus log of 25, using the second rule on that formula sheet. And log 25, of course, 25 is 5 squared. So I can end up writing that as log to base 2 minus 2 log 5. Because it's log 5 squared and the 2 can come to the front. And of course, that's now in terms of a and b, we've got a minus 2b. So this is not really difficult. It's quite good fun, actually. You've just got to be able to split things out, find the patterns in the numbers. This example, we're now being asked to express a in terms of b, and again that's just about rearranging so that we can see what the value of a would be. So in this first question, 5 log a equals 4 log b. So what I really want to do is to try and get log a on its own so I can see what the value of a would be. So let's divide by 5. Log of a equals 4/5 log of b. And of course I can use the power rule to bring the power back up. So log of a equals log of b to the power of 4/5. So now I can equate a with b to the 4/5. That was nice and straightforward. Even though the answer looks complicated, the process was nice and easy. A equals b to the power of 4/5. Second one, log a equals log b minus log 2. Well, let's bring everything together here on the right-hand side using the second rule there. Log a equals log, well, hopefully you now know this, log b over 2 because it's a subtraction of logs. So that just means that a must be equal to b over 2. Easy peasy. No problems there. And then the third example, rather like an earlier example in this video, where we've got a number, it's often useful to turn that back into a log so that we can manipulate it with it. This is also more complicated, this question, because at the moment the expression is for log b, but we want to express a in terms of b. So let's do a bit of rearranging first and get log a on its own. 4 log a, taking it over to the left hand side, equals 1 minus log b. And I now want to get rid of 1 and write it in log form. Remember, this is to base 10. We haven't got it written down there, but by default the word log without a base is in base 10. So 4 log a must equal, well, log to base 10 of 10 is equal to 1, because 10 to the power of 1 is 10. And then I've got log b. Now I can bring those together. So I've got 4 log a equals log of 10 over b, because I'm doing a subtract there. And then I can divide by 4 by 4. So log a equals a quarter log of 10 over b. And then I can use my power rule here and say that log of a equals log of the whole thing here, 10 over b, all to the power of a quarter. So a must be equal to 10 over b to the power of a quarter. A little bit more complicated there, but just use the rules and make sure you don't make any silly maths errors. Hope I didn't make any there. I'm sure you'll tell me if I did. Last but not least, we might get a proving or show that type question. And in this one, I wanted to show you this example because we haven't used the change of base rule so far in these examples. And you can see in the example that I've just given you that we've got log to base x and log to base y in this example. And our first reaction should always be to try and get everything into the same base. It doesn't really matter in this question whether we choose to go with log to base x or log to base y. We could do it both ways, but let's put everything into log to base x. So the first thing I'm going to do is take this second expression, log to base y of xy, and the change of base rule would tell me that's log to base x of xy over log to base x of y. Just using the formula down there at the bottom of the formula sheet. Now I've got that, I can rewrite this expression. I've got 1 over, and I'm going to split the expression out. Log to base x of xy can also be written as log to base x of x plus log to base x of y. And on the other side, well, I can, I've got 1 over log to base x of xy over log to base x of y. So I can flip that fraction and make that log to base x of y on top and log to base x of x plus log to base x of y. Now, of course, you hopefully notice that I could rewrite log to base x of x as 1 just to make things easier here as well. So if I do that, I've got 1 over 1 plus log to base x of y plus log to base x of y over 1 plus log to base x of y. Wonderful. And if I bring those together, I end up with 1 plus log to base x of y all over 1 to base log to base x of y, which indeed equals 1. We got there. All these questions, there are potentially 2 or 3 or 4 different ways of tackling them. There's no right or wrong. We're just using the laws and trying to stay consistent. So just be careful with it, and no great secret apart from just practicing and practicing, I guess. So there we go. In the next video, we're going to look at solving equations with logarithms. But that was a bit of a useful thing just to show you what kind of tactics we use to bring things together or to split them out, because that will be essential when we're solving as well. Hope you found that useful. Thank you for watching. Don't forget to like this video and subscribe to my YouTube channel, IB Maths Intense. Tell your friends I'm here. Drop me an email at ibmathsintense@gmail.com. And don't forget to keep enjoying your maths, and you take care.